Welcome to this explainer. Today, we are diving right into a classic laboratory dilemma that sits at the absolute heart of analytical chemistry. You see, in chemical analysis, and specifically in gas chromatography, we're constantly playing this high-stakes balancing act between speed and quality. But as you'll see, finding that balance isn't just some guessing game. It is a highly precise, measurable science. So let's start with a really fundamental question. What actually happens physically if you try to rush a chemical separation? Well, our intuition completely screams at us that rushing is going to ruin the results. And, intuition is absolutely right about that. But here is the fascinating twist that trips up a lot of people. Our intuition almost completely fails to predict the danger of going too slow. Okay, let's lay out our map for today. We're going to cover 1, the speed of separation, 2, meet the Van Deemter equation, 3, A, the packing term, 4, B and C, the kinetic tug-of-war, and finally, 5, finding the sweet spot.
Section 1, the speed of separation.
Now, in a lot of the earlier relationships used to express how a separation works, the speed of the mobile phase actually didn't even appear. It was completely left out. But obviously, the progression of solutes through a column isn't instantaneous, right? The mobile phase is traveling at a specific speed, and that speed is a physical reality that directly alters how your molecules disperse within the column. These are kinetic considerations. If you don't account for how that velocity affects dispersion, you simply cannot optimize the ultimate quality of your analysis.
Section 2, meet the Van Deemter equation.
So the crucial point is, how do we actually wrangle all these messy kinetic realities into something we can control? Well, we use a famous formula proposed by Van Deemter. It was first used in gas chromatography and actually later expanded to liquid chromatography via the Knox equation. The simplified form is just beautiful. H equals A plus B over U plus C times U. H stands for the height equivalent to a theoretical plate, or HETP, and U is the mean linear velocity of our mobile phase. Those experimental parameters, A, B, and C, they represent distinct physical forces. And just to keep our math straight, if H is measured in centimeters, A is in centimeters, B is in square centimeters per second, and C is in seconds. Section 3, A, the packing term. Let's break down that first variable. Term A is known as the packing term, and it's intimately related to the flow profile of the mobile phase as it traverses the stationary phase. You can kind of think of it as an environmental hazard or an obstacle course. You've got stationary phase particles in there, and their size, their dimensional distribution, and how uniformly they're packed, all of that creates preferential paths. It causes an improper exchange of the solute between the two phases, a phenomenon known as eddy diffusion or turbulent diffusion. Interestingly, though, if you're using a WCOT, a wall-coated open tubular capillary column, this term is absent by definition, which gives us Goulet's equation without term A. Section 4, B and C, the kinetic tug-of-war. All right, now we get to the core tension of this whole explainer. Terms B and C are essentially two competing physical forces locked in a kinetic tug-of-war. Let's look at term B first. This is your diffusion coefficient in the mobile phase, specifically longitudinal molecular diffusion. And it is incredibly important when your mobile phase is a gas. Term B is literally just a consequence of entropy. As the text perfectly puts it, a system will tend towards the maximum degrees of freedom as demonstrated by a drop of ink that diffuses after falling into a glass of water. And this brilliantly illustrates why you have to be so careful. Look at the left side here. If your flow rate is too slow, term B completely takes over. Entropy wins out, and your compounds will literally mix together faster than they migrate down the column. This is exactly why you must never, ever interrupt a separation process, even momentarily. But look at the right side. If you rush it and push the flow too fast, term C dominates. Term C is the resistance to mass transfer. The diffusion of your solute between phases is not instantaneous. If you rush the gas, you create local turbulence and concentration gradients, meaning there's absolutely no time for equilibrium to be obtained. Your solute gets trapped in a non-equilibrium process. Section 5, finding the sweet spot. Now, what's really interesting about this slide is how it visualizes the solution to that tug-of-war. Here is the famous Van Deemter plot. That straight, dashed horizontal line, that's term A, which doesn't really care about velocity. But look at the curve dropping sharply on the left, that's term B, showing that massive penalty in efficiency when you go too slow. And the straight line rising up to the right is term C, showing the penalty for rushing. But when you add them all together, you get that solid, dark hyperbolic curve. See that deep dip right in the middle? That is H min. That is the absolute, magical, Goldilocks sweet spot where your flow rate is perfectly optimized. So how do chromatographers actually find this in the lab? Well, they don't just guess. They'll conduct several experiments for the exact same solute, just running it at different flow rates. Then, they use a mathematical method called multiple linear regression to match those experimental values and find the specific hyperbolic function for their setup. Once you map that out, you can locate the exact minimum. And here is perhaps the coolest part. Essentially, this resulting curve does not depend on the nature of the solute. Ultimately, analytical chemistry is all about balancing these incredibly strict opposing kinetic forces. By understanding the Van Deemter equation, we're not cheating physics. We are simply mapping the mathematical boundaries of entropy and mass transfer to find that perfect operational zone. So in the constant battle between resolution, speed, and capacity, which will you sacrifice next? Thanks so much for joining me on this explainer, and I hope you keep questioning the physical forces behind all your data.